Okay, we are live on YouTube. Welcome everybody to this IQS quantum discussion. It's been a while since we've done one. Actually, since we started these, the campus at Chapman University has reopened, and so now we're back to doing in-person public lectures as well. But I enjoyed doing these discussions so much that I've decided to continue them. So we'll be doing about 3 quantum discussions per semester, and there's a theme. So this semester there's a theme, which is, I would say, maybe unusual ways to get around Bell's theorem is the theme, right? So normally, according to conventional wisdom, Bell's theorem implies one of 2 things. One is that you should forget about scientific realism altogether and go sort of full-blown Copenhagen and be anti-realist about things. And the other conventional wisdom is that if you want to be a realist about quantum mechanics, then you have to have non-locality. Just bite the bullet and have straightforward non-local influences. But there are other assumptions in the theorem, and there are other ways out which are getting sort of increasing attention, I would say, in recent years. So I'm going to be talking with people this semester who take those kind of routes. Later on in this semester, I'll be talking to Sabine Hossenfelder, and also much later on in the semester, I will be doing the first one of these with local participants at Chapman University. I'll be talking to Kai Wagel and Kelvin McQueen a lot about multiple universe solutions to non-locality. But today, I'm talking to Rod Sutherland from Sydney, who is a well-known advocate of retrocausality, which is influences that travel backwards in time. So welcome, Rod.
Hi.
So I wanted to start off with sort of get a bit of background information about your background in this area. So how did you get into working on the foundations of quantum mechanics in the first place, especially given that it's a somewhat unusual thing for a physicist to do? And how did you decide specifically that you were interested in working on retrocausation?
Yes, well, when I came to do my PhD, I'd already decided that this was a very interesting topic and I'd like to work on it. Unfortunately, there was a very flexible academic staff member at the University of New South Wales who was willing to take it on because he was interested too. And so I just simply chose the topic myself and launched into it. As to the retrocausality, working on interpretation of quantum mechanics, you soon run into things like Bell's theorem. And it just seemed to me, since I was very strongly wanting to hold on to special relativity, any form of locality, so any form of non-locality was going to be very contrived and artificial to me. So the alternative, if you're going to maintain realism and a clear picture, was to allow the communication between the 2 separated particles to travel along the obvious connection between them, which is the backwards world line or the zigzag going from one back to the original point where they separated and then forward to the other particle. So that just seemed to me a natural sort of explanation for Bell's theorem. And having done that in the PhD, I continued on to explore possible mathematical models on that once I was finished and became a lecturer myself.
Right, so, oh, I'm getting echoes now. Oh, that's better, okay. So what would you say? So you've mentioned the resolution of non-locality and the maintenance of special relativity, and those are probably the main advantages of thinking about a retrocausal framework. But are there any other things that you would emphasize as reasons for taking this seriously?
Yes, certainly. Yeah, I mean, the first 2 things are to avoid the non-locality, and secondly, to maintain Lorentz covariance, keep special relativity, and that's keeping it even at the hidden level. I mean, quantum mechanics is already compatible with relativity at the observable level, but if you're going to have some underlying physical reality, you want that to be compatible with relativity as well. And so the obvious way to do it was, in my opinion, was to go down this path. But two other things that have emerged since then are, firstly, you can avoid the configuration space description for the many particle case. In one particle case, it seems okay to use a wave function, but running with a wave function in 3n dimensions is certainly not a good step towards realism. And fortunately, if you include final boundary conditions as well as initial ones, allowing them to have an influence as well, then suddenly the whole picture reverts back into the normal 4 dimensions of space-time, and you avoid any ontology being in configuration space. So that's one advantage. But another obvious advantage as well is that, I mean, quantum mechanics is all statistical. No matter how well you do your measurements at one time for the boundary condition, you're never going to pin down a value for every known observable, and you're forced to work with statistics. But if you say, oh, well, we just haven't included enough boundary conditions, if you put in both the initial boundary condition and the final one, then everything can become definite and deterministic in between. And suddenly it's a lot easier to work mathematically with that sort of picture. For example, if you're trying to build a quantum gravity theory, suddenly you've got rid of the statistics and you can work with a definite theory, certainties. And so there other values have emerged along the way as to why this would be a favourable attempt to try.
Yeah, so I just wanted I want to expound on a couple of those things, since I want to try and keep this accessible to as wide an audience as possible. So the configuration space issue, just to clarify, if you're talking about the quantum mechanics of a single particle, and we often do this in popular accounts, you can think of the state of the quantum system, the wave function, as being a wave in physical space, you know, a bit like very similar to a wave on water or something like that. But as soon as you have two particles, that description is no longer in ordinary three-dimensional space, but in a much larger space that gets, that isn't physical space. So somehow you have to find a way to get a description of what's going on in ordinary three-dimensional space from this sort of very abstract object that lives in a much larger dimensional space. And so that's the issue here. So what you're saying is that if we have retrocausality, we can work with things that exist in three-dimensional space and are much easier to sort of understand in terms of the real goings on in the universe, if you like.
If I could just expand on that point, yes, this many-dimensional function that you have to deal with in the many-particle case, suddenly you can get back to a separate wave function for each particle, provided you put in the final boundary conditions. So suddenly you are reducing the wave functions back to separate ones. Of course, we don't have access to that because you'd have to know the knowledge of the latest boundary conditions, which we don't know yet. But mathematically, it makes it a lot more convenient to have separate wave functions. If you're building any sort of hidden variable model or interpretation of quantum mechanics in that way, having a separate wave function for each particle is mathematically much simpler, and you can use it to have a separate field for each acting on each particle. Or anyway, there are obvious advantages in being able to do that.
Yes, okay. So I do want to talk a little bit about some of the specifics of some of the theories that you've worked on. But before we get there, I was wondering if you could say a bit about the reaction you've got to the idea of retrocausality, because I'm aware that you have talked to some of the luminaries of the field about the idea and what they thought about it. So what kind of reaction have you gotten?
Well, often it's quite an open-minded one. I think you're referring to the way I handled my sabbatical leaves in the early days, which is different from other people. Instead of just going to some particular place for 6 months and doing research, my approach was a bit different. I'd make a whole bunch of questions, maybe 10 pages of them, and then I'd pick out people around the world that I'd like to talk to them about it. And then I just travel from one place to another, continually dropping in on well-known people and seeing what their opinions were and asking questions. in a lot of cases, the answer was, yeah, they're fine with retrocausality as long as it led to something useful, which of course is naturally the whole point. There were a few exceptions. John Bell, for example, was not that keen on the idea. David Bohm thought that, you'll notice that all these people were alive then, and so I was able to drop in on them. And I guess I was a bit bold because in most cases I just rolled up and knocked on their door without making an appointment. But they were both people who were a bit dubious about it. Bohm felt it might restrict the free will of the observer, but other people were friendly towards it. Let me just think of a few names. There was Roger Penrose. You'll notice I only pick big names to drop in on in this sort of thing. Basil Hiley, of course, still alive and kicking, and he seemed to be quite happy to sit on the fence and accepted it was okay. Henry Stapp. I had intended to even try and drop in on Richard Feynman, but he unfortunately died just before I launched into this sabbatical trip. But undeterred, I rolled up. I said, I'll leave Caltech on the list, and I rolled up to where his office was and knocked on the door next door. And of course, the door next door belonged to Murray Gell-Mann, the inventor of quarks. So I asked him to. So along with a lot of other questions, I wasn't just pushing the retrocausality attitude, but there was always an open-minded attitude to these things. And so I wasn't getting a lot of pushback at all.
Yes, okay. Well, that's interesting. I would have thought that there would be more, right? I would have thought that there would be amongst the luminaries of physics just a more of an attitude towards conventional wisdom. When was it that you were asking these questions? What year was it?
Two separate sabbaticals, 1987 and 1989. The 87 one, I visited the Institut Henri Poincaré in Paris, and Vigier was in charge there, and he arranged for me to go and see John Bell over at CERN, which was kind of him. I wasn't just dropping in at CERN, fortunately. And so that was in 87. In 89, I wandered around a whole lot of different universities in the United States. So they were the sort of years. There were probably good times to do it because a number of these people died shortly after. So it was the right time to be getting in there.
Yeah, so one has to wonder what some of these people would say now, especially given that the number of the profile of the field of quantum foundations is a bit higher now than it was back in the 1980s.
I should say, yes, that if there was any pushback, particularly in the late 70s when I was doing my PhD, the pushback was against the entire idea of looking at the foundations of quantum mechanics instead of sort of shut up and calculate. There was the attitude definitely changed there. And so, it wasn't so much the retrocausality at all. And in any case, people I spoke to since then have actually thought about going down this approach themselves. It's all very well. You need some answer to Bell's theorem, and people who prefer the more straightforward, realistic pictures see this as one of the least harmful options.
Yeah. Okay, well, so maybe we can talk a little bit about some of the theories that you've looked at and the differences and similarities between them and other things that are also going on in research right now. So early on, or at least up until a few years ago, you were looking at theories that are a bit like de Broglie-Bohm theory in the sense of involving particles having definite trajectories, but instead of being guided just by a wave function that comes from the past, there is also an influence from future conditions. And then I read a recent paper of yours a couple of days ago where you talk about instead a theory which has a ontology of densities. So instead of having particles with definite trajectories, you now have, for example, a mass density. So an electron its mass might at some point in an experiment be spread out along multiple paths or multiple locations. So I was wondering if you have a preference between those two views, and what's the reason that you had for switching to look at the density type of ontology recently?
Right, yes. My attitude is that I'm happy to sit on the fence and have either particles or fields as the underlying reality. I tend towards keeping four-dimensional space-time and as the background, because this relativity is so well supported experimentally, and there's not the slightest contradiction of that. So I'm not rushing to take that away. But once you bring in space as one of your assumptions, things are either going to be localized or spread out. And so the particle one is the localized one, and the field type ontology would be the spread out one. So I've tried both, and in both cases, I was essentially using a similar sort of mathematical formalism, and and both worked reasonably well. So I'm sort of still sitting on the fence. It's interesting that sort of after all these years, and certainly after 100 years of wave-particle duality in quantum mechanics, I'm still not sure whether to go for an underlying ontology of fields or particles. Probably the field one is more easy to generalize to quantum field theory. On the other hand, the particle one has certain advantages for the theory of measurement, in that whereas you're wondering why you get a definite result at all with measurements in quantum mechanics, given that it ought to just evolve by the Schrodinger equation and make the apparatus fuzzy instead of getting a definite result. If you've got a particle there, it clearly chooses one of the options, one of the paths that can go down, and it makes it a very simple solution to the measurement problem. So in that sense, favouring the particle one might be good. But again, you know, as I said, I'm happy to sit on the fence. The good thing is that there's this mathematical formalism that works in both cases, and is a very elegant and attractive generalisation of standard quantum formalism, which should be considered on its own, regardless of the interpretation, because it certainly is suggestive that this might be something that would be useful in the future.
Mm-hmm. Yeah, and I have to say that when I was reading your papers, I found the exposition extremely clear. It was very clear what was going on and what the description of the world that these theories give was supposed to be, and that isn't always the case. I have to apologize, by the way, although maybe it's appropriate for our sort of Halloween episode, but the lights in my office go off if you don't wave your arms enough. So hang on a second. There we go, we're back. Okay, so yeah, so I was just wondering if you had a preference between those two, but let's talk about, it seems like you don't, so let's maybe talk about...
No, in fact, I'm just about to put up another paper, and I sort of back it both ways even in that. So yes, so I'm not, in any case, even if you have a particle picture, if the particle just moved the way it did in straight lines in classical mechanics, then it wouldn't be giving the quantum mechanical predictions. You really need some sort of field there in a particle picture to push the particle in ways that will be consistent with the quantum mechanical predictions. So it's really a choice between field only or particle plus field. I don't think the particle on its own is going to hack it.
Right. So I wanted to talk to you about sort of another issue in the way that we go about, that we sort of talk about retrocausal theories these days, because there's been sort of quite a lot of work done on it, and well, I say quite a lot. There's a few people who are interested in taking these kind of models seriously, and there seems to be sort of two distinct ways that people talk about it, which, to my mind, I'm not sure if they are ultimately the same, or they'll ultimately turn out to be equivalent, or they'll be fundamentally different. So the way that you like to talk about it in your papers, and the way that a number of other people, including Yaki Aharonov, who's here at Chapman, like to talk about it, is in terms of boundary conditions. So you have, in the standard formulation of quantum mechanics, and indeed many other physical theories, you have an initial condition that in principle is set at the beginning of time, at the beginning of the universe, so some state, some initial state, which then sort of evolves forwards in time. And that's true in a theory with that, that's one way of formulating a theory that doesn't have retrocausality in it. So one way of breaking out of that picture is, of course, to say, well, as well as there being an initial condition at the beginning of time, there's a final condition at the end of the time, and this one evolves forwards and this one evolves backwards, and they somehow meet in the middle, and that determines what happens at that point in time. So that's one way of talking about it, and that's the way that you've like to construct things in the paper. There's another way which I like to use, and certainly a few other people like to use, like Emily Adlam and maybe even Hugh Price. I'm not exactly clear on what his view on this was, although it certainly was inspired by a particular model that he came up with several years ago. And that's, I talk about it more like a sort of jigsaw puzzle type of approach. So the idea here is that, we normally think of physics with causality in terms of sort of input-output relations. So you put in a state and then do some process on it and get out a state at a later time. So instead of that, you sort of make that whole thing more time symmetric. So it's like, you construct what happens in space-time a bit like a jigsaw puzzle. So I put down a piece of a jigsaw puzzle that places constraints on what other pieces can go next to it. And if you think of this as the forward direction of time, it equally constrains what happens earlier as to what happens later. So a choice I make to put down a particular piece here constrain locally nearby constrains what can happen. And in that picture, you really don't talk about anything evolving forwards and backwards in time. You're talking about what's happening just in the block of space-time, as it were. And one thing that's not clear to me, I sometimes like to think about it, is whether these two approaches are somehow equivalent, whether you could take the sort of jigsaw puzzle approach and always bring everything down to initial and final conditions or not. It's certainly, on the top of my head, it certainly seems like, on the face of it, those are different concepts. So maybe you can say something about that and why you've chosen to prefer the approach that you do.
I'm not sure that the two are that different. Certainly when you talk about moving forwards or backwards in time or propagating, I certainly wouldn't talk in that sort of language. I don't see any sort of movement in space-time. To me, it would be the same as if, we'll take the three-dimensional case, which I think has been quoted before, of two charged plates. Just in the normal world where it's completely static, nothing changing, and there's a charge distribution on each plate. If you just look at one plate and use the charge there to calculate what the electric field might be halfway between the plates, you're going to get the wrong answer because you've only used one boundary condition, which is the plate on one side. You've got to include the charge distribution of the other plate. We'll assume they're dielectric, so the charge doesn't move around. You've got to include charge distribution on both plates in order to get an accurate calculation of the field in the middle. So in that sense, to me, it's all just the same as if you were working in 3 dimensions with a static case. I'm certainly not suggesting there's any sort of propagation in forwards or backwards in time. I'm just treating time as very similar to a spatial dimension. Concerning the jigsaw one, I hadn't actually heard that before, so I'll have to read up on that. But I'm not aware of any differences between Hugh Price's views and mine. So I suspect we're dealing with much the same thing here.
So what I'm talking about is, and you're probably familiar with this paper, there's the paper on the Helsinki model, which is several years old now. Are you familiar with that one?
I doubt it, but keep going.
It's one of Hugh Price's papers, and it's not it's not meant to be a full model of quantum mechanics, but sort of a kind of toy model for how you might go about constructing a theory with retrocausality. So he has these sort of, it really is in some sense, like I said, it's sort of jigsaw puzzle pieces that have to fit together in space-time in a certain way. So that's like, for me, that was the influence for thinking about these models in this particular way. But anyway, maybe that's something we can talk about on another occasion if you want to read about those things. But the other thing, I just wanted to clarify. Although I'm talking about the boundary condition idea in terms of a state evolving backwards and a state evolving forwards. Clearly, that's not sort of how you're supposed to think about these theories fundamentally. You're supposed to think about it as, that the laws are constraints on what happens in four-dimensional space-time, right? So I agree with that picture. It's just a question of, the difference is, I think, a question of how those laws are expressed as constraints. So
when you say, it's okay to take the wave function and mathematically evolve it forwards in time. That's really just for convenience. You're moving the boundary condition to a different point because it's more helpful to have it at the midpoint between. And the same, you can mathematically evolve the final boundary condition backwards in time using, say, the Schrodinger equation. But that's certainly not meant to suggest that there's any flow going on in physical space.
Yeah. So I agree with that. So I'm not trying to get at a distinction between sort of that and evolution. It's sort of just a distinction between how you view the laws of the theory as being formulated in terms of constraints.
Yeah, well, one of the things that's very convenient if you want to go down this path is, instead of using the conventional idea of the mathematics of classical physics, where you have say a differential equation and you use that to state some boundary conditions and evolve it forwards in time, a much more appropriate mathematics for discussing this sort of retrocausality is to use variational principles and Lagrangians, which where you automatically tend to state initial and final boundary conditions even in classical mechanics. Instead of stating, say, the position and velocity of a particle at the beginning, you can equally well state the initial and final position of a particle and work out everything in between. And all of this was done, back in the 19th century and earlier. And it didn't need quantum mechanics for us to have this as a very convenient and elegant mathematical approach. And using the Lagrangian, which I have done, it's wonderful, because once you get to the Lagrangian, and which I've done in this case, one that's time symmetric, so it includes the final boundary condition. Once you get this, you can predict everything. The Lagrangian will give you conservation of energy and momentum. It'll give you the field equations and the equations of motion. And you can solve everything you want, all from this one single scalar expression. And so that certainly is mathematically the way to go if you want to consider retrocausality. But calling it retrocausality may be a little bit confusing anyway. I wasn't wanting to be too causal in the whole thing. I was more just thinking of that you need both the final as well as the initial state in order to completely specify what's in between, which would be the way in which quantum mechanics was unique and different from classical mechanics. Excuse me.
Yes, so I have to agree that causality and cause and effect per se are sort of loaded terms and require some analysis. I do think that there is a way of making sense of this kind of picture as genuine causation, but maybe I'm going to leave that for a more philosophical type of discussion.
I'm looking forward to when you put it forward, actually.
I want to instead pick up on something about that you mentioned about mathematical formalisms. So this is the issue of how do we really know that we're dealing with I don't want to say retrocausality because of the objection, but backwards in time, shall we say backwards in time influences of some type rather than something else, because of course as you've mentioned, even in like every physical theory that we have has multiple different mathematical formalisms. And if you think about classical mechanics, some of those mathematical formalisms are more closely tied to what we think is really going, if classical mechanics were true, there would be a certain picture of reality that was correct. And that picture of reality has things like particles that travel in along definite trajectories, and it has as well fields that exist in space, and these evolve. So we don't think that there's any necessity for retrocausation in classical mechanics. On the other hand, there are different mathematical formalisms. So as you mentioned, there's the Lagrangian formalism where you do impose initial and final boundary conditions. There's also just the fact that the regular equations of, say, classical mechanics that you learn in university or high school even are time symmetric. So I can equally well say I specify the state of the system at some earlier time, and then I determine mathematically what happens at a later time, and that looks like regular forwards in time causation, if you like. But there's also, since I have time reversal invariance, I can equally well say I specify the state at some later time, and that determines what happens at an earlier time. So you could say, well, the theory is completely backwards in time, right? So the question is really, how do we know that in these theories of quantum mechanics that we're coming up with, that what we're really dealing with is retrocausation versus just something that looks like retrocausation in a particular mathematical formalism? So I was wondering if you had any views on that.
Well, excuse me. No matter what mathematical formalism you choose, you're still going to be faced with the non-locality problem in Bell's theorem. If you want to preserve special relativity, you're going to have to go to something like this. And so this is a convenient way of avoiding such problems. But there may well be different mathematical formalisms for describing the final answer when we find it. But I think all of them will I'll be faced with the same situation. Concerning I should just clarify what we mean too with the statement about just what effect the observer is having when causing a backwards in time effect. All the observer does is choose which particular observable quantity to measure, what type of measurement to perform. The argument is that this may be having an effect on the earlier state. The reason that this seems plausible is that things are quite different from classical mechanics in that we've got the uncertainty principle. And we learn two things from the uncertainty principle. Firstly, we learn that no matter how well we do our measurements at one time, we can't get a definite value for all the possible observable quantities, and some things will be left open. So this leaves open the possibility, it leaves room, unlike classical mechanics, for some things to be partly determined by what's coming later. Secondly, we learn from the uncertainty principle that when we measure something, we don't just learn a value, we irretrievably change the state as well. That's unavoidable, which means it wouldn't be so far-fetched to suggest that our final measurement is also not just getting a result, but changing the state as well. And if it changes it backwards in time, so between the two measurements, then there's an excellent chance that you can pin down a completely definite theory.
Okay, yeah. I have some follow-ups on this, but we did have a question coming in from the chat room, so maybe we can deal with that first. Otherwise we may not get to it because I'm going to get lost in the things that I want to discuss with you. So somebody whose name I will not, who's at least YouTube username I will not try to pronounce, wants to ask about your discussion with Costa de Beauregard. So what happened?
Yes, well, I did meet him in person back in 1987 when I was at the Institut Henri Poincaré. He'd already retired, but he made a special train trip down from where he lived in the countryside to come and see me, which was nice of him. And so we had a good chat about it. He was an excellent fellow and a real gentleman, and he was very careful to acknowledge everyone else with the work they were doing in this area. Incidentally, back in those days, there had been, you said that only a few people worked on this. There were dozens and dozens of people who were suggesting, hey, mate, this might be the way out back in those days. The only thing different about Costa de Beauregard that intrigued me was that he suggested the zigzag method of solving Bell's theorem, much the same as other people. But then he said, but I fully agree with the Copenhagen interpretation and I don't support realism. And this surprised me because I still can't quite understand why he felt the need to give an explanation of Bell's theorem at all if he wasn't aiming for a realistic model underneath. But certainly that was what I can still remember that came out to me from that short discussion I had with him. And the same thing is reflected in several letters of exchange between him and I. He was very enthusiastic that anyone would take the retrocausal idea forward, because he, after all, was the one who first thought of it right back in the early 1950s. And so he was keen to see that people were wanting to go down that path. So he was quite encouraging, because I was quite young then, of course. And so he was giving plenty of encouragement. And I was still exchanging letters with him, even after that density model you mentioned, which was published in 1998. He asked for a copy of it and was enthusiastic about it. And so there was letters being exchanged even then.
Yes. So I mean, for those who don't know the background history of this, Costa de Beauregard was a PhD student of Louis de Broglie, I believe, and he's one in response to the EPR Einstein-Podolsky-Rosen paradox, which sort of first introduced what we now call the concept of an entangled state, and used that to it's the whole history, that development up to non-locality and Bell's theorem. So in response to that, Costa de Beauregard proposed what we now sometimes call the Parisian zigzag, because he was in Paris, which is just this idea that the influence travels from the detector back to the source and then back up to the other detector, right? So, and he, as far as I know, he was the first person to propose this. I don't know if you know exactly if that's true, if anybody else was thinking along the same lines at the time.
I'm aware there were hints going right back to the late 1920s, I think, from Eddington, but I mean, only in a very sparse idea that maybe something like this was going on. But I think Costa de Beauregard is definitely the one who pinpointed the zigzag. That's all due to him.
Yes, and was it true that he had this idea for a long time before he published it, because de Broglie was not keen on him writing
yeah, well,
this
I
article?
understand so, yes, that de Broglie basically said, don't go down this path, don't publish it. But then they read Feynman's zigzag method of doing quantum field theory, with positrons being electrons traveling backwards in time. And once that became a sort of acceptable thing to talk about, de Broglie relented and said, all right, yes, maybe you should put it in, maybe you should publish it after all.
Right. Okay. Yeah, the history of this is very interesting, because, for a very long time, this kind of idea has been sort of fringe, although there has been, as you mentioned, there has been, even in classical theories, the Wheeler-Feynman approach to electrodynamics, at least mathematical formalisms have been proposed a lot, in which it looks like, at least naively looks like, there are backwards in time influences. So it's not a particularly unusual idea in the mathematical formalization of physics, but just sort of thinking about this seriously in sort of realist approaches to quantum mechanics has, at least until quite recently, always been a very fringe idea. Maybe is still a fringe idea, I'm not quite sure. At least more people, when I mention the idea, people don't seem to say I'm as crazy as they might have done a few years ago.
I noticed, looking at my papers on archive, one paper that clearly talks about backwards in time, particularly to explain the Klein-Gordon current density, the 4 current density, which is it's not positive definite, so it looks as though you can't use it as a probability distribution, but you can easily place an interpretation on this if you use retrocausality. The reason I mention it is that particular paper has over 1,000 reads, according to ResearchGate. So there's clearly people out there who are interested in looking down this path. So I just thought I'd mention that. It's not just a few fringe people looking at each other's papers. There's clearly large numbers of people who are interested.
Yeah, when I give talks on this subject, which is not by far not the only kind of approach I work on, but when I do give talks on this subject, I try to compile a list of different authors who are currently working on it, and the list does seems to be growing quite rapidly. I do want to bring in actually another question from the chat, because it's a clarification of something you said much earlier. I think it might help for some of our other viewers as well to address this. So yeah, earlier you talked about preserving consistency with special relativity at the ontological level, and so someone is asking, what do you mean by that precisely? So I think like if we can contrast what it means to preserve special relativity at the operational as opposed to the ontological level and explain what that means, that might be helpful for some people.
Okay, well, probably the easiest way to do that is in terms of the Bohm model, which basically just suggests that as well as the standard quantum mechanical formalism, there are really particle trajectories going on. So the particles exist in between measurements, not just when we measure them. It's well known that quantum mechanics, the standard theory is, of course, completely compatible with completely compatible with special relativity. But as soon as you start being in this hidden picture that there are trajectories even when we're not looking, it's not possible to make that sort of model compatible with relativity. We can't see these hidden trajectories, but if we assume they're there, then the standard Bohm model runs into the trouble that when you do a measurement on one particle, it has to make a change to the trajectory of the other particle at that time. And then you run into the difficulty, what do you mean by at that time? Because you're choosing the preferred frame of reference. On the other hand, if you bring in retrocausality, then the states of the particles are the same right back to the initial point where the two particles separated. And so you don't have this problem of sudden changes on a preferred frame of reference down at the hidden level. But of course, it is all hidden. If you want to, you can just say, oh, I'm only interested in what we can actually measure, not on what sort of underlying reality there is. And then if you do that, then you're fully compatible with special relativity.
Right. Yeah, thanks for that. There are more. I'm gonna push some more of the questions into the Q&A section because there's a couple of other things I'd like to talk about. So in particular, I mean, I try to address this without getting too technical, but it's something that I've wondered about and I'm not clear on entirely in these theories. So sort of fundamentally in this kind of theory, you want to talk about, arguably an initial condition at the beginning of the universe and a final boundary condition sort of at the end of the universe. When we talk about a particular experiment, say we're analyzing the double slit experiment, we talk about an initial state coming, just from the beginning of that experiment and a final state coming from sort of the measurements that are done at the end of that experiment. Now, in a sort of conventional theory without retrocausality, where you have the forward evolving state, I think I understand how it is that I can avoid having to talk about the initial state at the very beginning of the universe and can make do with just sort of talking about a state that refers to the beginning of this experiment at this particular time that I'm starting it, right? And it has a lot to do with thermodynamics and the arrow of time, and the fact that I'm capable of preparing a system in a particular state, partly because I have a supply of low entropy systems that I can do that with. So my question is really, is there sort of an analogous thing that you can say about the final boundary condition? So why is it that it's okay for me to just talk about the boundary condition at the end of this experiment? How is it that I know it will be the right sort of thing to sort of behave in the way that we want it to, just representing sort of the choice of measurement and the measurement outcome? Do you have a question?
Yeah, it is. I'll have a go at answering it anyway. I mean, it's true that in most of the stuff I've written for convenience, I've just taken the two boundary conditions to both be the initial state preparation before we do a measurement, and then taken the measurement that we take as the final boundary condition, and using those two together work out what must have existed in between. Theoretically, you should be able to push it right out to the end of the universe. I'm not quite sure that you need to worry about thermodynamic considerations. If we're just talking about a single particle here, I suppose you can think of some sort of wave function representing the final state of the universe, whatever that might be, flowing or evolving right back. But I think by the symmetry of the mathematics, you should be okay in just taking it from the moment of the second measurement backwards. Because whenever we do a measurement in quantum mechanics, we know that you start again with a new state from that point, and that's completely sufficient to make all the predictions you need. You don't, when we're doing the initial state, we don't have to worry about, oh, what about the measurement before that and the measurement before that? Yeah. We don't have to take them into account. We've just got a single state to work with, summarising everything we need to know from that time onwards. As far as I can see, it should be possible with the next measurement to do the same thing and say that's overruled anything further in the future. We can just take that and evolve that back to find out what's in between.
Yeah, so it's not entirely obvious to me whether that's true, right? So I mean, basically what you need somehow is to be able to say that this region of space-time in which I'm doing this experiment is sort of sufficiently isolated from everything else that I don't need to worry about it, right? And, you know, I at least think that it does have something to do with thermodynamics, because, you know, why is it that I can sort of, you know, in order to make an experiment and to set up the initial conditions of an experiment, I need to be able to sort of isolate it from everything else. And, you know, one of the reasons I can do that is that I can do things like cool down a system to make it go into a particular state that I can more or less regard as you know, the lowest energy state, for instance, and or I can discard systems into the environment, right? You know, it's basically, the thing is that it seems like I need it seems like I need a supply of low entropy systems that I can sort of swap in order to sort of make sure that my system is sufficiently isolated from things that had happened in the past. Now,
you've opened up a really good research field there, and I fully agree that that's not fully understood. I think we can probably get away with what we're doing, because it is an isolated system just between the two measurements that we do, the initial one for state preparation and the final one. But yes, I mean, you've opened up a really good question, but I'm not going to be able to answer it, I don't think.
Here's my concern about it, right? So here's the thing that's a real concern. And there go the lights off again. Never mind. We'll go into Halloween mode for a minute so that I can get. So yeah, so we know that you know, on the conventional account, in order to get the universe that we know, the initial state of the universe has to be a rather special one. A rather special one, you know, that in the sense that it's going to be low entropy, but it's still nonetheless, we hope, if we have an elegant theory, that the initial condition of the universe would be something simple to specify and understand, right? So we have the laws of the theory and we have the initial state, both of which we hope would be sort of simple, elegant, and sort of easy to specify. My worry is that in order to get what we need to happen with the backwards evolving state, that the final boundary condition of the end of the universe might have to be something very complicated that is difficult to state, and sort of it seems like we might have to you know, there might be a sort of simplicity argument against the idea if it turns out that the final boundary condition of the universe has to be something that's sort of difficult to specify. That's the worry I'm trying to get at, really.
I guess so, but we don't know what the final boundary condition of the universe is at all at this stage. It's pure speculation. It might be something simple. There may even be going back to zero entropy again. If we're going to have retrocausality, it does even open the possibility that the entropy will increase to a certain point and then may even decrease again. So there's so many options here available, speculative ones, that I wouldn't want to rush to say that this was going to be ruling out the ideas of what we're looking at just in the narrower sense in the laboratory.
Yeah, but so what I'm getting at is not, I don't want a full theory of the initial and final conditions of the universe. Obviously, that's would be great, but it's possibly a bit much to ask for. But there must be some sort of general things that you can say about that can be said about what the final boundary condition has to look like in order to get it to behave in the kind of way that you're using in your papers. So it's like
the main thing I think that would need is to assume that whatever is representing the particle, whether it be a real particle or a field, it needs to be reasonably localized at that later stage and spread as you evolve in the backward time direction. I mean, in the forward time direction with the normal wave function, if you do a measurement, it might split into several branches and evolve forward and never be recombined again. But you never see a situation where the initial or the normal wave function is already in the state of many separate branches and suddenly merges for the first time as you're going forward in the laboratory. That would be most unusual. So likewise, if we take the time reverse situation, you can expect that the wave function evolving back from the future will be localized and then might spread into branches as it goes through a measurement. That in itself should be enough to make sure you get a definite measurement result rather than a whole lot of fuzziness.
Mm-hmm. Okay, yeah. So I mean,
that's the one point that I would say is needed, but I'm not aware of anything else that would be needed to fit in with the measurement results of quantum mechanics.
Okay, I think it's something I'd like to think about a bit more in the future, but I was just raising it as a possible issue. I guess there's one last topic I want to touch on. We have a few people. There's at least one question in the chat room, so we will go and do a Q&A in a few minutes. But I wanted to touch on, we actually haven't talked too much about the details of Bell's theorem itself. It's something that I've talked with other people about in these discussions before. So, I don't want to go too much over the details of that. But there are, of course, a whole host of other no-go theorems that are now people study, including quantum contextuality and more recently things about the reality of the wave function. And there is a hope, at least amongst some of us, well, me definitely, that by looking at these more sort of, I'm trying to avoid using the word exotic possibilities. But that's sort of the technical term I use for things that don't fit into the standard framework. So by looking at these more exotic possibilities, we might also be able to get around the constraints of those other theorems. And in particular, I'm thinking about the reality of the wave function. So in the models that you've proposed, to my mind, that issue is made even worse, right? Because we need to have two real wave functions instead of one, and I wasn't happy with that either. So
can I just pick you up on that? I don't see it as two different wave functions, especially not in the sort of mini particle case. What I see it as two different boundary conditions. The wave function is just a mathematical way of summarizing the initial boundary condition, which is what it is in standard quantum mechanics. You do your state preparation and you describe it by a wave function. So yes, I'm not suggesting that these are real waves by any means. It's true that for convenience, you can having declared your two boundary conditions, you can mathematically evolve them towards each other to the point in between where you want to know what the reality is. But that's a mathematical thing. They're certainly not being treated as real waves. They're just boundary conditions to me.
Yeah, so it's not sort of the question of treating them as real waves so much, but just do those boundary conditions represent ontological features as opposed to being something closer in spirit to probability distributions. So for example, I don't really mind mathematically what you do, but to determine, let's take the sort of Bohm type trajectory model to determine the trajectories of the theory. What's you say, okay, the fundamental reality is these particles moving along trajectories. But in order to determine how they're going to move in space-time, that's a function of both the actual you need to know what the what those two wave functions are in order to calculate that. So in that sense, they're ontological in the sense that they play a role in the laws, which you think of as constraints on what the trajectories are, right? So and that's very different to the point of view which says, well, these wave functions, I should think of them as somehow more like statistical things. They're analogous to classical probability distributions, which is the kind of view I prefer. And so there is a hope that you could use retrocausality to try and get this view to work in light of the no-go theorems. So but anyway, I just sort of wanted to get your sense on the relative importance of these other no-go. I mean, I know special relativity is a big thing, but do you have views?
Having looked at these other ones, as far as I can see, the retrocausal approach escapes from all of them. I mean, all of these no-go theorems basically assume that it's only forwards in time. And so you've got the usual problem that you've got with Bell's theorem, and it crops up with these other ones as well. But it seems to me that the retrocausality is a loophole that gets you out in every case. So I don't really see a problem. As to your comment about, sorry, if you want to make one more thing.
No, go ahead.
As to your comment about the wave function, yes, I'd like them to be interpreted as closely as possible as probability distributions too, but we've got to stick to what the experiments show, and basically their wave functions are complex quantities. They're certainly not positive definite, so we have to get somehow from them to the probabilities. The really good thing though is with retrocausality that once you do state these two things, you get rid of probabilities completely. Remember, stating the initial and final boundary conditions, you then have definite values, not statistical values in between. And so that simply means that you've improved matters out of sight.
Okay, so this is a fascinating discussion, and I think I could continue talking to you about this for ages, but I think I do want to conclude the main part of the discussion fairly soon and get on. We've got at least a couple of questions come in, so I'd like to move on to the Q&A if we can. So I am going to let my beautiful assistant Kai Wagel bring in questions from the YouTube chat room, and also I believe he has one of his own questions. So Kai, would you like to?
Yeah, we'll start with the one from the chat. Thank you for commenting on my beauty. I appreciate that, Matt. The question we had from the chat was, can you elaborate on what you said earlier about how retrocausality provides an interpretation of negative quasi-probabilities?
Sorry, say that again. I didn't quite catch it.
You had mentioned something earlier when this question came in about how the retrocausal model provided some clear explanation of negative quasi-probabilities in a distribution, like a negative Wigner function. Can you elaborate on that?
Well, yes, particularly I think I was talking in the context of the Klein-Gordon current for current density, which normally the time component of that would just be a probability distribution, but it comes out to be negative. But if you interpret the current density literally, it's simply meaning that the lines in space-time are going forwards in time, then backwards in time, and then forwards in time. This is standard quantum mechanics. This is not retrocausal, but such a thing becomes quite reasonable to understand if you're allowing retrocausality, because instead of talking about a single particle and then suddenly creation of a particle-antiparticle pair here, and then these two annihilate and one goes on, you can describe the whole thing in terms of a single particle. Of course, you would worry that all of this would be observable, but if you have a retrocausal theory, it's easy to show that once you've stated the initial and the final boundary conditions, there's no way that you can actually observe this turning backwards in time of a particle. And so it's provided you allow retrocausality, there's an easily physical interpretation of the Klein-Gordon current equations. And so it makes although it is similar to the Feynman idea of the Feynman zigzag with positons being electrons turning backwards in time, except he's got a zigzag with sharp corners. This would just, the Klein-Gordon one is smooth in the flow, but nevertheless, it's the same sort of idea. And so the retrocausality, fortunately, protects you so that the final result doesn't show up any of this having taken place in between. It may be happening like that, but once you impose the final boundary condition, that makes sure that the particle goes back to behaving itself as you get closer and closer to the final result. And so it's gone back to being a well-behaved time-like forwards in time world line. And so this protection comes automatically from using retrocausality.
Thank you. Another question we have here is it clear that you can avoid the PBR theorem with retrocausality? Just to be sure, is this because you're denying setting independence or freedom of choice, or is there something else to it?
Yeah, well, I haven't looked at it for a while, but yes, I was convinced at the time that it avoids it, and I've spoken to colleagues and they're of the same opinion. I think that's the assumption, yes, that's the key one, yes.
Okay. And then I had a question about what you were saying about kind of related to this, about the reality of the wave function. You're talking about an initial and final boundary condition, kind of telling you everything you need to know. Weak measurements, and in particular weak values, which are conditional, weak measurements conditioned on that future boundary condition, they're coupling some other detector to the system in between the time of the preparation and the final measurement. But the coupling is in principle so weak that it doesn't really perturb the system. So what do you think is being measured by that kind of a device in your kind of explanation?
Well, I noticed with the weak value type arguments that have been put forward in all the papers, my impression is that the people involved, excuse me, are sitting on the fence as to what the underlying physical reality is, or the ontology. They're talking about what you would get with the measurement. I'm not sure whether Aharonov has taken a definite stand on this. I'd like to know, actually, that's a good point. But from my point of view, I think it would be good to assume that this really is measuring something that's there. So in other words, the weak value is giving us a hint of the actual hidden ontology underneath. So I would certainly see it that way, particularly for most observables. It may be a little bit difficult with the case of position. If you're using a field model, you don't have to worry about position, but it's and I would be inclined to say that this is indicating that all of the observable quantities really do have a hidden value there, and but normally we don't know what it is.
Yeah, I work with Yakir Aronov on this subject, and I can tell you that, yeah, I think that the idea of an underlying ontology, something that you can actually measure, is the direction he's going, but the theory is not really fully down yet. So, yeah.
I just wanted to follow up on that a little bit, because something that we didn't talk about. Of course, there are, it's not just you who has an approach based on retrocausality or symmetric boundary conditions. So I wonder if you could sort of compare or contrast your approach with some of the other well-known approaches that take this point of view, like, for example, a transactional interpretation. We've briefly touched on Yakir Aharonov's type of approach and other things like that.
Well, the transactional one was one of the early attempts on this, and it's a good thing, but it's actually around the time I was first thinking about it too. The reason I haven't gone down that path is that there are some things that worry me a little bit there. Firstly, the transactional one seems to require movement backwards and forwards in space-time in order to set up a transaction, a handshake. So this seems to be introducing some sort of back and forward motion within space-time, whereas there's meant to be everything's meant to be static and no motion in space-time. So it's going outside the normal space-time picture, which concerns me, unless in the absence of any extra experimental evidence to point us in that direction. I'd rather have a simpler model where you simply work with the existing space-time and special relativity. The other things are with that model, I don't mean to be too critical here too. I mean, I'm full marks to everyone who's attempting models in this area, because no one has found the right solution fully yet. But the other thing is that model involved adding retarded and advanced waves together. So it's an addition. But if you try to generalize the model to the many particle case or to quantum field theory, mathematically it doesn't go well if you've got a sum of two different functions. It works a lot better if you've got a product, and that's what I use and what's been used by other people such as Aharonov and even another gentleman called K.V. Roberts, even earlier back in the 1970s. I think he's the first one to have mentioned this formalism. So that's another thing. Also, there are dangers too with causality paradoxes. I don't want to take a definite stand on this, but I'm aware that people like Tim Maudlin have come up with paradoxes that this might be more prone to than the later retrocausal models, which mainly talk about what exists between measurements, and so they're not in such danger of being picked up by a causality paradox. So that's the transactional one, but nevertheless, the basic idea was good, just as Costa de Beauregard's even earlier basic idea was good. What other model do you want me to comment on?
I don't know. I think that's sufficient. Another thing you could comment on, of course, because you alluded to it earlier, is the big goal of all of physics, the theory of quantum gravity. How do you think this kind of model might help in formulating a theory that incorporates? Let me put it this way: I'm not going to call it quantum gravity. I'm going to call it a theory that incorporates both the standard model and gravity together. How do you think this might help?
Well, I'm not claiming that it would solve all the problems, but it is true that something like retrocausality opens up whole new avenues that haven't been explored. And there's clearly one thing going on here that's good about it, and that is that when you just try to go to a naive attempt at building a quantum gravity theory, if we look at Einstein's field equation for general relativity, on the right-hand side, we have the source term, the energy momentum tensor. This is a definite quantity in classical physics, but once you go to quantum mechanics, it becomes an expectation value. It's just giving average values, and it changes discontinuously, instantaneously once there's an update from a measurement. It's really not going to be able to be used literally in building a gravity theory, because it would mean when you did a measurement, the gravitational field on the left-hand side of the equation would discontinuously change. And this is making it a little bit difficult to build such a model. But if you go to the retrocausal theory and you state both the initial and the final boundary conditions, suddenly you've got a definite energy momentum tensor. No statistics, just a nice simple source that you can use, and it won't change discontinuously. It's already got fed in what the next measurement result will be. So we've got something smooth to work with. It won't change in any way that makes it mathematically difficult. And if the right-hand side of the Einstein field equation now becomes definite, there's no need for the left-hand side to go statistical either. So we can have a definite gravitational field. Now, I'm not suggesting that's the right way forward necessarily, but it shows the enormous simplification that can be introduced just by using retrocausality. We get to something where you can work with a definite space-time pre-existing without having to invent it and make it evolve out of the whole theory. It's certainly, you might call it naive. In fact, I wrote a paper saying naive quantum gravity to point this out. But the whole point is that simplifications that people hadn't even thought of do get introduced once you allow this extra degree of freedom of the retrocausality.
Yeah, thanks for that. I think there's another couple of questions in the chat, Kai, and then after that, I think it's probably time to conclude. So, Kai, do you want to follow up with the questions?
We have another. What relationship do you see between the causally symmetric Bohm model and the two-state vector formalism?
Well, yeah, I mean, the two-state vector formalism is using two state functions just the way I'm using in the Bohm model. But my Bohm model goes further and says, yes, I'm taking the ontology, the physical picture, seriously. I'm being in a particle. The two-state vector formalism doesn't have any particles, trajectories, or world lines. It's just using the two things together to give more information about what sort of measurement results you could get with a weak measurement in between. So I guess I'm taking it seriously and saying, yes, well, let's see if we can use this to actually get an underlying physical reality. And I try both a particle one with trajectories, and I try a more field-like one where you've got densities of energy and momentum and quantities like that. Either way, you're getting a definite ontology, which you don't have with if you only go to the two-state vector formalism.
Yeah, one connection I can make for the audience there is that in the two-state vector formalism, you've still got wave functions of the usual configuration space type. You're not yet talking about something that's in regular, normal three-dimensional space. All right, and there's one more question which is related. Is non-commutative geometry compatible with this retrocausal model, your retrocausal model?
That's not a field I know much about. That's really asking a lot of me. It may well be, but I just can't comment because it's one of the many good, promising possibilities to be tried.
Yeah. The aim of these discussions was to try and keep things at a as general audience accessible level as possible, although I know that we have a lot of specialists in our audience as well, so I'm happy to talk about that. But sort of ending talking about non-commutative geometry is probably, it may be a bit much for some of the people who are watching this. Okay, I think. Yeah, is there anything you'd like to conclude on, Rod? Is there anything that you feel you'd like to tell people that we haven't covered in our discussion so far?
I think we've done a pretty good in-depth coverage, actually. I was running out of ideas to convey at this level. I'd just like to thank you for giving me the opportunity to talk. This has been fun, and I'll be watching your shows in the future now that I know about them.
Well, thank you very much, and thank you very much for agreeing to do this. And I know I had to reschedule you a few times, so thanks for putting up with that. Okay, I think that's the end of the discussion for today. I just want to mention upcoming next week. It will be on the same day, but at 8:30 a.m. but Pacific time, so much earlier in the morning for people. That's when I'm going to be talking to Sabine Hossenfelder. Of course, that's too early in the morning usually for me to get up and do physics, but I will grin and bear it for everybody else. And you can always watch the video after the fact. So that'll be the next one happening on Wednesday, October the 13th at 8:30 a.m. Pacific time. Okay, so thanks everybody for watching, and hopefully we'll see you at the next one. Okay, bye everyone.